Welcome, everyone. As we move our machine learning models from manual experimentation to automated production, we need the rigor of software engineering. Today, we will master how to manage machine learning source control using Git and GitHub. Welcome to our first topic. What exactly does source control mean for machine learning? Traditionally, data scientists worked in isolated notebooks, leading to lost code and untrackable changes. By applying Git, a version control system, we treat our ML code, infrastructure configurations, and even our AI prompts as software code. The basics are simple. Git tracks every single change made over time in a centralized repository. Why do we need this? It ensures reproducibility. If a newly deployed model breaks, you can instantly roll back. How? We host our repositories on platforms like GitHub. For a deep dive, consider that in modern AI, a single word change in a system prompt can drastically alter an agent's behavior. By versioning prompts and configs in Git, you manage them with the exact same rigor as traditional software. Look at this diagram comparing ad hoc workflows to Git-based workflows. On the top, ad hoc ML leads directly to lost code and environment drift. But on the bottom, our Git-based ML branches out into three powerful capabilities: maintaining a strict version history, enabling secure team collaboration, and acting as the foundational trigger for automated CI/CD pipelines. Before we write a single line of code, we must structure our repository correctly. What is a repository structure? It is the logical organization of your ML project files. The basics involve strictly separating your exploratory Jupyter notebooks from your clean, production-ready Python scripts. Why is this critical? Because automated CI/CD pipelines rely on predictable file paths to trigger the right training jobs. How do we do it? We create dedicated folders for our source code, infrastructure YAML configs, and GitHub Actions workflows. Delving deeper into modern GenAI, we store AI prompts using standardized formats like plain text or Markdown. This ensures that when a prompt is updated, a human reviewer checking the pull request can easily see the side-by-side differences in the Git history. This tree diagram maps out a best practice repository structure. At the root, we have our GitHub repository. Notice how it branches into highly specific directories. We have src for our Python code, config for our infrastructure as code YAML files, prompts for our text-based AI instructions, and the crucial .github workflows folder where our automation pipelines live. Let's discuss how we actually update code using feature-based development. What is it? It is a Git strategy where developers work in isolated branches. The absolute golden rule of ML source control is this: no one is ever allowed to push changes directly to the main production branch. Why? Because pushing an untested hyperparameter or a flawed system prompt can instantly break your live applications. How do we enforce this? When a data scientist wants to tune a model, they branch off from main, creating an isolated feature branch. Here is the deep dive. Once their experiment is successful, they don't just copy the code over. They open a pull request, or PR. This PR acts as a secure staging area where peers can review the code and automated tests can execute before it ever touches the main codebase. If you look at this Git graph, the solid line represents our main production branch. A data scientist needs to tune a model, so they check out a new branch called feature tuning. They make their commits updating the learning rate and testing it. Crucially, the code only merges back into the main branch after a pull request is formally approved, ensuring production remains pristine. A branching strategy is useless if it isn't enforced. This is where protecting the main branch comes in. What are branch protection rules? They are GitHub settings that physically prevent unauthorized code merges. The basics involve rejecting any direct pushes to the main branch. Why do we need this? To enforce a zero-trust environment and ensure that every single code change passes a strict quality gate. How do we set this up? In your repository settings, you require at least one human peer review and mandate that automated status checks must pass before the merge button even becomes clickable. For our deep dive, we link these rules directly to our ML metrics. If an automated script evaluates your new model and its accuracy drops below an acceptable threshold, the status check fails and the pull request is automatically blocked. This flow illustrates the branch protection gatekeeper. When a pull request is opened, it hits our branch protection rules. It must satisfy two parallel checks, a mandatory human peer review, and passing automated tests. Only when both conditions evaluate to yes is the code allowed to merge into the main branch. If either fails, the merge is completely blocked. As your project evolves, you will manage dozens of models and prompts. We need a strict versioning strategy. What is this? It is the practice of explicitly tracking specific iterations of your ML assets. The basics involve using Git commits and Git tags to mark significant milestones, like a release candidate. Why is this vital? Because if your model starts hallucinating in production, you need to know exactly which code version is running to execute a rapid rollback. How do we do it? When a pull request is merged and deployed, we tag that specific Git commit with a version number, like version 2.1. Deep diving into operations, this Git tag creates a perfectly traceable link. If an auditor asks why an AI agent made a certain decision on a specific date, you can look up the exact prompt version in GitHub that was active at that time. This state diagram tracks the lifecycle of an ML asset. It starts as a draft during local editing. Once pushed, it becomes a pull request. After approvals are met, the state transitions to merged. At this exact moment, we apply a version tag, like version 1.0, which then triggers the final transition into a deployed endpoint. Source control isn't just about storing code, it is the engine for automation. We achieve this by triggering ML workflows with Git events. What does this mean? We use GitHub Actions to automate tasks based on repository activity. The basics are simple. You define workflows that wake up when a specific event occurs, like a pull request or a code push. Why do this? Because manually running deployment or training scripts is slow and highly error-prone. How is it implemented? You write declarative YAML files in your repository that instruct GitHub what to do. For a deep dive, imagine a data scientist updates a hyperparameter and opens a PR. This Git event instantly triggers a GitHub action, which securely reaches out to Azure ML and automatically spins up a compute cluster to train the new model, validating the code before a human even reviews it. Observe this automation flow. It all begins with a Git event, specifically a pull request. This event triggers our GitHub action YAML file. The workflow first authenticates securely to Azure, then submits an Azure ML training job. Once the job finishes, it gathers the performance metrics and posts them directly back into the pull request comments for the team to review. To make that automation work, we must connect GitHub to Azure, which brings us to securing the integration. What is this? It is the process of securely authenticating your Git repository to your cloud workspace. The basics are that automation tools cannot use your personal email and password. Why? Because hard-coding credentials in your scripts will inevitably lead to a massive security breach. How do we solve it? We store credentials securely using GitHub secrets. Taking a deep dive into enterprise security, we use an Azure Service Principal. Even better, we use OpenID Connect, or OIDC, for federated credentials. This means GitHub Actions can securely request a short-lived access token from Microsoft Entra ID without us ever having to store or rotate a permanent password in GitHub. This sequence diagram maps the highly secure OIDC authentication handshake. The GitHub action requests a token from Microsoft Entra ID. Entra ID verifies the request and issues a short-lived, secure token. The GitHub action then passes this temporary token to the Azure ML workspace to trigger the training job, ensuring a totally passwordless, secure transaction. Let's tie this all together with a real-world use case. Prozware, a healthcare startup, maintains a critical diabetes classification model. They need to update this model frequently as new data arrives, but they cannot risk breaking the live application. Using what we've learned, they implement a strict Git workflow. When a data scientist updates the pre-processing logic, they do it on an isolated feature branch. They open a pull request, which triggers a GitHub action. This action trains the model and posts the new accuracy score. Because branch protection rules are active, a senior engineer must review the PR. Once approved and merged into the main branch, a final GitHub action automatically deploys the model to a staging endpoint. Git becomes the absolute single source of truth, seamlessly bridging human collaboration and automated ML operations. Here is Prozware's end-to-end MLOps pipeline. The data scientist works on a feature branch and opens a pull request. This triggers the action to train the model. We hit our branch protection gate, do tests pass, and is the peer review approved? If yes, the code merges to main, which triggers the final deployment to staging. If no, the pipeline halts, protecting our application.